Hello everybody out there in YouTube land. Good times for all here, Zachary Zabala if you prefer. In this video, we're going to be talking about the differences between how an electric field will act on a spherical object and how it will act on a plane. All of the information I'm going to share with you I got from Walter Lewin, the former MIT physics professor, his 802 electricity class here on YouTube. Lecture number 3. It's actually his actual class, but he calls it 802. That was the actual physics MIT. So lecture number 3, still into Gauss's law and how things work on a plane and a sphere. And there is 3 different things we're going to look at. We're going to look at how it would act on a sphere, how it would act on an infinite plane, and how it would act on just a shorter plane. All right. So to start off, we're going to work with the sphere here, and I'm going to kind of draw in a experiment that he did. Now, to start off with, on a sphere, the way things work, the electricity will diminish in the inverse square law, which, if you want the equation, it's 1 over the radius squared. And the radius is from the center point. It doesn't matter where you are on this surface. Anywhere you take from, it's as if it's from the center. That's how they do it in physics. So you have your point spot and your radius out. The inverse square law, instead of doing the math, I'm just going to show you how he did it in the experiment. It's much easier to understand this way. So say you have your sphere here, which is charged. Okay, doesn't matter positive or negative. We'll just say that this is positive, okay? And you have a balloon hanging on a mylar balloon hanging on a string and a rod, okay? So when the balloon is this far away, here we're going to make that angle a lot more actually. It'll be just so you can get it. And actually, no, this will be charged positive too. If it was negative, they would be attracting each other. So you have a positive here, the same charge. Now we're right on it, okay? We are, but. We're going to pretend like that is right on that, okay? So from 0 millimeters away, your angle is whatever. We'll say this. We're just going to, I know it isn't, but we're going to say that this is an 80 right now, okay? From right there. So you have your 80-degree angle. Now, if you were to move it, we're going to actually write down the 80-degree down here. From 0, you get an 80-degree angle, okay? 0, we'll just say millimeters. Now, say we go out here. And your distance here is 10 millimeters now. So you have 10 millimeters there, and your angle drops down to a 70. So at 10 millimeters, it would be 70 degrees. Well, I don't even need to, we'll just leave that there. Then we come way out here. We'll just say that don't even really need to change stuff around. I don't know why I am. Now we're going to go out to 20 millimeters, okay? So now it's 20 millimeters. Inverse square means at 20 millimeters, from 0 to 10, it moved 10 degrees. So from 10 to 20 millimeters, it's going to double. So now this would be 50 degrees. And then you go to 30 millimeters, and it would double again, 40, so you would have 10 degrees. So the further away you get, the greater the electricity drops off on a sphere. That's the inverse square law. So it pretty much doubles. Well, not doubles. It's a mathematical formula. But yeah, it drops off very fast. Now, let's say you had an infinite plane. I don't even really need to draw anything here. It's very easy to explain. The force, we're going to say it's positive. This is positive. It doesn't matter how far away you are. It could be 10 millimeters. It could be 100 millimeters. This angle right here will always be the same on an infinite plane. The field, it doesn't weaken. Whatever it is right here on the plane, you can go up any amount and it will be right here the same as here. That's Gauss's law. Okay, and now the interesting part that I thought is what happens when you get to, and there's a way to do the math, but you just have a small plane. It's going to drop off, okay? But it will not be at the inverse square law. It drops off very slowly. There's ways to do this. The math is much more complicated. It's in the inverse square law. But pretty much it's saying that it will drop off. But it's not going to do it at such a rapid rate. It will slowly. When you go away 10 millimeters and then to 20 millimeters, it's not going to double just by moving it double the distance. It's not. It might only go down, a couple degrees. And then a couple degrees more. And then it might not actually at first, for a certain barrier, it will be the same, pretty much. And then once you get to a certain point, then it'll slowly start to gradually, and eventually it will come to the 1 over r squared. Once this plane right here, this giant, however big it is, starts acting like a point source, like a sphere. Remember how I said it doesn't matter where on the sphere you are, it's a point source. So you take it from the center of that source. They kind of say in physics, well, the whole part of the sphere is all equal on the outside edge, if it is a perfect sphere. Now, I don't know if any of this stuff is actually true or not. I've seen some experimentation, but as far as the whole, when they wrote a lot of these laws, I think they made things just to make the math simpler. But that's it, kind of, folks. So, it raises the question in my mind is, we have a negative field here that diminishes as we go up. The field gets less and less and less. So does this mean can we measure it to see if it is a point source? If the Earth is a sphere, does the electric field drop off at 1 over r squared? or does it do as it would? Now we know it drops off, so at least the electric field cannot be an infinite plane. If what they are saying is 100% correct and accurate. I'm not saying that there can't be an infinite plane. I'm saying that the electric field is not infinite. Whatever is causing the electric field. So, do we live on a plane? Is our electric field a plane that diminishes at a certain rate? Or does it drop off at 1 over r squared, the inverse square law? Now, this should be able to be seen. Now, we don't know as far as the numbers they give us. We've already seen with people doing high altitude balloon launches that they're lying about the temperatures. The temperatures they're giving us are not how it actually is. So I'd like to see people who are going to be doing balloon launches. If you have the extra money, let's see if we can't measure the electric field and see how quickly it diminishes, or if it diminishes at all. So, but yeah, I think we can test to see whether or not we live on a sphere, an electric field that is spherical, or an electric field that is a plane. Infinite or not, we can test. And this is real experimentation here, folks. This isn't theoretical. So that's it. It's already way too long, but I just wanted to share that with you guys. 802 Electricity, Lecture 3. Walter Lewin, former MIT professor. He understands this stuff very well, and he explains it so, a child could understand it almost. It's amazing, and the experiments are just wonderful. You should check it out if you're interested in electricity. So that's it. Good Times for All here, signing out. As always, thanks for watching.